So this next session is about GIS-based mineral prospectivity mapping and spatial data analysis for exploration targeting of mineral deposits. It's a bit different from all the talks we have had since morning, but ultimate aim is to find new deposits or at least areas for more exploration. So we will start this session with the keynote talk by Alok Porwal, and it's mainly about how we can use different machine learning methods for mineral prospectivity mapping.
Thank you, Bijal. Yes, so it's going to be difficult to talk about machine learning with petrologists and geochemists, but I'm sure that there will be something for you to get out of this presentation. So the whole idea is, as Bijal just pointed out, we want to find a mineral deposit. So starting with the global scale, and we are progressively narrowing down our search area to the deposit scale. So this scale issue is critical when we are doing or narrowing down or finding areas for our projects and for deposits. So starting with the global scale, where there are geodynamic settings, the whole lithospheric architecture that becomes important. Then from there you move into the province scale, where probably tectonic settings, the scale in the history that becomes more important. And then you go down to district scale, where lithostructural setting becomes more important. Finally, you go down to the project scale, where the precipitation mechanisms, or what you call the trapping of metal, those processes become more important. So this is about prediction of mineral deposits versus detection of mineral deposits. And if you look at this plot here, we find that so as the area reduces, the prediction becomes less effective and detection becomes more effective. But if I look at the costing and the flexibility, so the price or the cost of direct detection is prohibitive when I'm working at a province scale or a district scale. And it's only when I go up to the project scale where the direct detection techniques that become more important. On the other hand, when I'm at the province scale and try to find areas for projects, that time the predictive modeling or predictive techniques, they are much more important. But the flexibility, as you are reducing your area, it reduces. And that is why prediction part of the process is very, very important. Because once you commit yourself to a project scale, you already spent a lot of money, and now you cannot afford to go out of it very easily. Whereas when you are at the prediction or the province scale or campus scale, you still have flexibility because you have spent most of your time on computer trying to figure out where are the potential targets. So there you can very quickly change your areas. So again, coming back to this triangle, and what we find is that we are typically here at the district to the camp scale. That's where we are looking at the processes, which includes the sources of the metals, the pathways for the metals, the traps of the metal, all the three components, they become important. And that's where we use GIS-based prospectivity modeling. So it's integration of the data sets that are typically on regional scale in order to delineate project size targets. Because once you are on the project size targets, then the next move is detection and moving on to ground and start your ground exploration. So now here it is the integration of data sets. So typically we are having geology, we've got geophysics, remote sensing, geochemistry, the typical data sets that are all available in public domain. We can dump them all in GIS, we combine and we get an output, but that doesn't work because our inputs have to be able to represent the mineralization processes at that specific scale. And that's why it's critical to identify our inputs correctly. And this presentation that I'm going to talk about is whereas the focus of the exploration targeting or prospectivity modeling has been on the integration aspect of it, the mathematical modeling aspect of it rather than the input aspect of it. So this time here, I'm going to focus why this input aspect is important and what we can do about it. So the whole process, it can be divided into three components. The first, of course, is the knowledge base, and that's where you are trying to understand the mineralization processes. You're trying to come up with a conceptual genetic model of the deposit that you're targeting. And based on that, you identify the targeting criteria. And once you have the targeting criteria listed out, identified clearly, then you move on to your GIS, where you got your exploration data sets. And then we sit down and we process our GIS data sets in such a way that they can capture the targeting criteria. So these are the spatial proxies of the targeting criteria or the mineralization processes. So that is the process that happens in GIS. And once we have all these targeting criteria or mineralization processes well represented in form GIS layers, the next step is to integrate them and then come up with an output that can be used for identification of our targets. So that's where we have been now getting interested into machine learning, because this is a part where we have got multiple inputs, and those multiple inputs, they have to be sort of combined, integrated, and machine learning is one good way where you got several different type of inputs with some known output. Then it becomes very effective to combine them. So typically, prospectivity modeling before machine learning became very popular, it started off by having a data, and we knew exactly what the model was. So we are providing the model to the computer, we are providing the data to the computer, and computer gives us the output, which is the standard way of modeling. Now, machine learning turned the problem on its head. So what we do is we are actually providing the input to the machine, and we are providing the output to the machine. And we are letting the machine work out the relationship between the input and output. And that is what we say, that's modeling, the model that relates the input to the output. Now, the assumption in the conventional prospectivity modeling is that the relationship between mineralization processes and mineral deposit formation and localization is well constrained. Whereas in machine learning, the assumption is that we really don't understand what are the processes which are actually controlling the localization of a mineral deposit at a specific point, which in fact is true. So there's a lot of uncertainty there. And that's why machine learning is becoming very popular in prospectivity modeling. So geological processes, they are poorly constrained. They are difficult. We normally don't have the data sets at regional scale through which we can see those processes happening, or whether they happened or not. It's difficult to predict. And that's why the model selection is difficult. We really don't know what is the relationship between the input or input are the data sets that we have, output is the mineral deposit. So we don't know what is the relationship between these two. And that's why model selection becomes critical. And what we typically do is our model selection is based on what kind of data sets are available to us. So if you've got lots, we are in brownfields exploration where there are already lots of deposits discovered, it's probably good to be using some kind of a data-driven approach where we use the analogs. We try to find the analogs of already existing deposits. On the other hand, we could be in a greenfields area where we don't have any existing deposits. So we have to start using some expert knowledge, try to give weightages to our different input GIS layers, and then combine them and generate targets. So machine learning is actually letting the data discover the model, and we are typically dealing with brownfields target where there are already a number of deposits occurring. But the main question is, and In fact, when I was preparing this presentation, I had in my mind an audience who's probably more machine learning and data science oriented, at least majority of them. But what I see is all geochemists and petrologists. So the key question here is, what is the machine really learning when I'm applying machine learning algorithms over GIS data sets and trying to predict deposits? So this is the flow chart. So I got my primary data sets, which come in form of gravity, magnetic data, radiometrics, remote sensing. It could be geological maps, structural maps. So these are the typical data sets at 1 to 50,000 to 1 to 250,000 scale that we are using for prospectivity modeling. Now, these data sets cannot directly be used in my model because, well, we really don't know what exactly is the relationship between the magnetic intensity value at a specific point to a deposit, whether that indicates a deposit or no. We can't do that. And that's why the first step here is that we extract the features out of these primary data sets, which is what we call feature engineering. So we are trying to extract features out of these primary data sets, and that step has to be done manually or visually. And that's what takes the most amount of time. You're interpreting your gravity data for anomalies, for structures, and something that you, a similar thing that you do with magnetic data or with remote sensing data. But this manual step, it gives us the features which are in fact the proxies of the mineralization processes as we understand our mineralization processes. And then we input into these features, we input it into our machine learning algorithm. And we use some kind of training data, which are the features that are associated with the known deposits to generate an output. That's a typical workflow for machine learning based prospectivity modeling. But the question that we were asking in the last slide was, what exactly is the machine learning? In fact, machine learning in this context is learning not the features, is not learning anything about the data sets because we are providing the features. The machine is simply learning the parameters of the model. So it's just trying to optimize the parameter to make the best predictions. And that's based on some kind of loss function that we can use. So this is the basic issue. Machine is not learning anything, although we are calling it machine learning, basically. So and I'm going to come back to this in a while. So the primary data sets that we're using are essentially of two types. The first are what we call the directly measured, uniformly gridded, sampled, and gridded data sets. So that would be airborne magnetics, it could be gamma ray spectrometric, gravity, remote sensing, topographical data. These are which have been sampled at regular intervals, and we can create a gridded map or image out of that. On the other hand, the second type of data sets, which we typically geologists use a lot, and those are the interpreted from the sparsely measured observations. So creation of a geological map itself is not a uniformly sampled process. You are actually measuring, you're reading at different distance intervals and trying to interpolate between them. And most of it is my interpretation versus someone else's interpretation. I'll do my geological mapping based on some assumptions, some understanding of the geology of the area, someone else would. These are where you have a high uncertainty because there is a subjectivity involved in that. And quite often we are using the primary data sets, particularly the geophysical data set, to create our geological maps. So essentially we are abstracting a lot of information from the primary data sets. So in the second type of data sets, there is a high level of abstraction and there is high uncertainty. And there is, of course, subjective bias, whereas on the first primary data sets, you really don't have any abstractions, just direct measurement with interpolation. Of course, when you're interpolating, you're making certain assumptions about the data set. So there is some uncertainty, which I would put as the stochastic uncertainty that's associated with the generation of data set. But these data sets, they've got much less uncertainty. So how do we select the features? And these are based on the conceptual models of the deposits that we are talking about. So what we are typically using at regional scale is what we call mineral systems approach. And I think that's pretty well established. So, the whole process is categorized into different critical components. So all of those components have to happen to form a mineral deposit. So you need to have a fertile source of metals, a fertile source of fluids. You need to have ligands that can, bring those metals into the fluid. So you need a source component, and then you need a pathway component, or what we call architecture, that can connect the source region for the fluids to the crystal near surface region, which can bring up the fluids. So that's the architecture. And the third is the overall geodynamic tectonic settings in which that mineral system can form. So these three components together, wherever there is a kind of intersection of the favorable sources, favorable architecture, and favorable geodynamic settings, that's where you would form a mineral deposit. So this, of course, this comes from Cam McQuaig and John Ronski's, which is, now this is just an example. I wouldn't get into all the details. It's done by Malcolm sitting there. So it's part of his PhD thesis. So this is about critical metals. So just take an example, he put together a mineral systems about the geodynamic settings where critical metals can form, then what are the fertile sources, what are the architecture that's required. So all of that then have been listed in form of this table where we have all possible processes listed out that can lead to the concentration of critical metals in specific part of crust or formation of critical metal deposits. So the major issue with this approach, which is theoretically very good because I'm connecting my processes to the layers, the data layers that I'm going to use for my modeling. The problem comes that most of the data sets that we have, they are at regional scale. It's not a regional scale, but I put it as more on camp to district scale, 1 to 50,000 to 1 to 250,000 scale. These are the data sets that we have, which are actually not capturing those processes, the precipitation mechanisms, because those are too detailed to be captured at low resolution. So what actually is happening in this whole pipeline for prospectivity modeling is I'm using deposits to train, but my data are not capturing the processes that form deposits. My data are actually capturing the fertile geology, the prospective terrains where I can find a mineral deposit, but it's not going to pinpoint a location where you'll find a mineral deposit. And there lies the crunch, because we are not using the right data for training. We are actually targeting not deposits, but the fertile geologies. It's kind of what I would say prospective tracts where you can find mineral deposits. But to find these tracts, it is not logical to use deposits, because deposits are actually reflecting something very different. And it was something that we analyzed over the Yilgarn craton, where we're looking at nickel sulfides, was that it is possible to predict where you would find komatiites, but within komatiites, where you're going to find nickel sulfide deposits, it was not possible to predict because they were randomly distributed within komatiites. Now, when I say randomly distributed, of course, they would have a control, but those controls cannot be read or seen in the data sets that I'm using. That means regional scale data sets. So that's where we move into deep learning, which is now becoming more and more popular. So the difference between machine learning, or what we call shallow learning, versus deep learning is simple. In deep learning, we are actually doing away with this step of feature engineering. So we are not letting a geologist and GIS expert to sit down and create GIS layers and features for us. We are just providing the primary data sets, our magnetic images and gravity images, nothing that involved the intervention of a human, and which have been directly observed. So we are providing these data directly to the network, and we are letting the network learn the features which are relevant, and then come up with the prospective ground. This whole process of identifying the features which are critical, for that you need deposits. Again, you need training points that can help the network, or that can lead the network to identify which features are critical. So we are letting the computer learn the representations of the primary data. We are letting the computer learn the features that are critical for formation of mineral deposit by itself. And for that, we are typically using what we call the convolution neural networks that involve not just looking at a specific pixel, but the neighborhood of the pixels. So essentially, idea is to capture not only the intensity value or the measured value at a pixel, but also the topological information. What is the relationship between, or between the value of one pixel to another pixel? In fact, we are looking at geometric and spatial configurations, which become critical, particularly when we are dealing with mineral deposit formations. So it could be a fault, it could be a lineament, it could be a magnetic anomaly, a circular anomaly, a curvilinear. So these kind of spatial features can be picked up by the convolutional network. So the problem, because this seems to be an optimal solution, because it is actually letting you not only save time, but you are actually letting the machine recognize. But the problem comes is that when I compare the shallow learning or conventional algorithms versus deep learning algorithms, they become more important when your data becomes really, really large. So it works very well with social media data for image processing. We've got a huge amount of data sets to work with. And when I'm dealing with prospectivity modeling, we've got very small amount of data. And the reason is the parameter estimation. The number of parameters that you need to estimate increase exponentially when we are dealing with deep learning. So this is the region where deep learning and other methods, they've got a huge difference in performance. They work much better, but this is the area where the traditional machine learning works better. So whether it is really useful or not? So we are actually looking at this part where mineral exploration data sets are typically residing. So, and that's where probably deep learning methods would underperform the normal standard machine learning method. So where we are using all different techniques to enhance our training data sets and all those things, but essentially we are simply fooling ourselves, because we are sampling or generating samples in the vicinity of the existing deposits. So it's going to be overfitting. We are actually just increasing the number of training samples without actually adding any new information to the network. So I'll very quickly skip this. So coming to solution, what can be done under these situations where you don't have enough training data, and we are never going to have enough training data for prospectivity modeling. So we have to move into something called unsupervised, where we really don't need the training data, and let's see what we can do with it. So one of the approaches would be using something like clustering techniques. We just cluster the input data and then identify which clusters are, analyze these clusters in geological context, and then identify which clusters are likely to be more potential. So here is an example. We got 4 primary data sets: the Aster remote sensing, gravity, magnetics, topography. We used the self-organizing map SWAM algorithm, and the idea was to just, this is the geological map on the right. This is the geological map that we are trying to recreate from these primary data sets without any human intervention, using the clustering techniques. And there are these deposits occurring there. This is actually this base metal from the Aravalli region of Western India. So what we get from clustering is this, which is definitely not what the geological map is, but it is very similar to that. And it is important because this has been generated using just those 4 data sets, where there is no ground geological mapping involved. Plus, it is also identifying these magenta clusters, which are containing most of the mineral deposits that we have in this. So the unsupervised algorithm has been able to capture the mineral deposits without any intervention, without any feedback coming from the geologist. And the second approach would be using something like encoder decoder. So we start with a magnetic image, we pass it through our deep convolutional neural network, and we try to recreate the image. So in the process of this input output matching, we extract out the features that are critical of this input image. And these are the features that we use for training, because they've got much lower dimension, and therefore there's less chances of overfitting there. So this is what we do. We start with the image, we convolve it over progressively larger filters, and we end up extracting out a sparse representation of the original image, not the entire image, but the critical features of that original image. And those are the features that we use for training, because the dimensionality is reduced, and therefore training becomes much easier. And that we use for generating. Just one more slide and I'm done. So this, again, very quickly, this is the experimentation we did. This is magnetic image, and these are the deposits. So this was the architecture that we used. We generated the sparse representation of this magnetic image, and that was used for modeling. And these are the sparse representation, dictionary of the sparse representations of this image. So these are the critical features. And these were trained using the deposits that we have, and that led to the identification of these prospective targets here in this image, which are typically capturing most of the deposits. And we did not use all the deposits for training. In fact, out of those 24, we used only 13 or 14 for training, and the remaining were kind of predicted by this model. So this is unsupervised deep learning, and particularly autoencoder decoder type of thing, where you can extract out the critical features and then train your system on these critical features to identify mineral deposits. That's probably going to work better. So to sum up, the new research in deep learning and machine learning should focus on feature extraction from primary gridded data, which then you can use to complement the knowledge-driven feature engineering. And new algorithms for data integration, I mean, we can use different techniques, different algorithms. They're not likely to give you any improved results for prospectivity modeling. That's the takeaway from my side. Thank you.
Geology map. But in my opinion, if we thinking about the deposit, maybe the supervised machine learning is maybe helpful, because, for example, we know maybe the high MJO number of the magma may be easy to form the magmatic sulfide deposit. Yeah, I think that it's our work on the geology maybe makes sense when we use the supervised machine learning. What's your idea about this?
Okay. If I get the question, are you asking when you can use supervised machine learning and when you cannot? Is that what? Yeah. Well, the simple rule of thumb is that if you're in the parameters or the input dimension or input number of layers that you're using for prospectivity modeling is less than, or I would put it the other way around, the number of deposits that you have is at least 3 or 4 times the number of layers that you're using, then supervised learning may work better, because here there's less chances of overfitting. Otherwise, your model is just going to find the deposits that are already discovered, and there's no point in that. So basically, the idea is to find deposits which have not been discovered. So this is what we call the difference between the specialized learning and generalized learning in this data science jargon. So yes, if you have got a large number of deposits, supervised learning might work. Yeah.
I use a approach to what you're describing the unsupervised machine learning for segmenting like spectrum